Welcome to the deep dive. It's really quite something, isn't it? What these general-purpose large language models, LLMs, can do now.
Oh, absolutely. Their scope is incredible. They seem to know a bit about everything.
Right. They tackle all sorts of language tasks. But
hmm
what happens when you try to get one of these sort of jacks of all trades to really handle the deep complexities of telecommunications?
Yes. That's where it gets tricky.
Yeah, that's where we see the limitations, right?
Definitely. The telecom world, it has its own very specific language, its own real-time challenges, things that these broad general models just aren't really built for.
So it's like they have a massive kind of shallow pool of knowledge, but not the deep well needed for telecom.
That's a good way to put it. Think about trying to optimize a complex network in real time, or diagnose a fault instantly, or even just automate configuration management accurately. These demand really nuanced understanding.
Which the general models often lack.
Exactly. They haven't been trained deeply on the specific telecom vocabulary or the, highly structured operational logs you find, or the really complex time series data that's so characteristic of this field.
Okay, so they might know about telecom, but they don't really speak telecom.
Precisely. And well, that's why we're diving into TSLAM Mini today.
Ah, the solution. Tell us about it.
So TSLAM Mini comes from NetoAI Solutions. It's a language model that's been meticulously fine-tuned specifically for telecommunications.
Meticulously fine-tuned. I like that.
Yeah. It's built on an architecture called 5.4 Mini Instruct 4B. Think of that as the engine. And it's actually quite compact, only 3.8 billion parameters.
Wow, okay, so not one of these 100 billion parameter giants.
No, but what's really interesting is the level of specific intelligence they've packed into that size. It punches above its weight, you could say, in its specific domain.
Okay, let's unpack this then. So instead of just hoping a general AI picks up telecom on the fly, NetoAI basically put a powerful but smaller model through intense telecom training.
That's the idea.
So our mission today really is to understand why this focused approach is so vital for telecom, and crucially, how TSLAM Mini actually performs compared to the big general models in this specific area.
Right. And also explore what it means for a model to have the intelligence of a network subject matter expert, or SME.
Yeah, that SME level intelligence claim is fascinating. This is probably key info if you, our listener, are trying to, get a handle on where AI is really making strides in the telecom space. Maybe prepping for a meeting or just catching up.
And a huge part of this, as you might guess, is the data it learned from. It wasn't just random web text.
Right, you mentioned bespoke data set.
Yes, a really tailored data set. 100,000 samples covering 20 key telecom use cases. And how they built it is quite clever.
Okay.
They use NetoAI's own DigiTwin platform. Think high-fidelity digital twins of networks generating realistic simulation data.
Ah, so creating realistic scenario.
Exactly. Plus, they fed it information from carefully processed RFC documents. Those are the technical rulebooks of the internet and telecom.
The foundational stuff.
Yeah, right. And crucially, they brought in seasoned telecom SMEs, actual human experts, to enrich and annotate the data.
So simulations, official standards, and human expertise. That sounds comprehensive.
It is. And this approach, as we'll discuss, seems to be surprisingly effective, leading to that SME-level performance.
Okay, let's dig into that first point, more the limitations of the general LLMs in telecom. You said it's an inherent lack of domain-specific knowledge. Paint us a picture.
Sure. So a general LLM, it's learned from, news articles, websites, books, a huge variety of text, but it hasn't lived inside a telecom network.
Right.
It hasn't seen thousands of specific router configurations or learned the patterns and obscure error logs from network devices or tracked how different routing protocols interact under stress.
It lacks the practical experience.
Exactly. So when you ask it to do something complex, like figure out the absolute best path for data traffic that's network optimization or pinpoint why a service went down based on a flood of technical logs, it often struggles.
It doesn't have the context or the deep pattern recognition for those specific tasks.
Precisely. And automating network configurations. That requires extreme precision. A mistake there, driven by a lack of deep understanding, could be, problematic.
Yeah, you don't want an AI making guesses when configuring critical infrastructure.
Yeah.
It really highlights the gap. They might know what a BGP session is, generally, but not the specific operational nuances or troubleshooting steps like an expert would.
That's a perfect example. It's the difference between knowing the definition and knowing how it works in practice under pressure.
And you mentioned the specialized lexicon, the structured logs, the time series data.
Yes, all areas where telecom is quite unique. The language is dense with acronyms and technical terms not common elsewhere. The logs are machine-generated, highly structured, need specific parsing, and the performance data, changing constantly, requires analytical techniques general models just haven't been trained for.
Okay, so TSLAM Mini was built to fill exactly these gaps. You said it's fine-tuned from 5.4 Mini Instruct 4B. What does fine-tuning actually involve here? And why start with that specific model?
So fine-tuning, think of it like this. You take a smart graduate, the 5.4 mini model, who has good general reasoning and language skills,
Okay,
and then you put them through a highly specialized, intensive training program focused only on telecommunications, using that bespoke data set we mentioned.
got it. So it specializes the existing intelligence.
Exactly. And the 5.4 mini DACE was likely chosen because it offers a good balance. It's known for being quite capable in reasoning and instruction following, but it's relatively efficient, not overwhelmingly large. That makes it a good foundation to build specialized skills onto without needing, a supercomputer for training.
Makes sense. Efficient specialization. And this training covered those 20 telecom use cases. Can you give us a taste of what those are?
Sure, the paper lists them out. It covers the absolute basics like network fundamentals, IP routing, how networks talk to each
The
other.
building blocks.
Right. Then it goes into specific technologies like MPLS, which is big in service provider networks. Network security, obviously critical. Automation is another big one, using AI to manage networks.
Right.
And it doesn't stop there. It covers the operational support systems, OSS, BSS, the mobile network side, both the radio access network, the RAN, and the mobile core. Even things like satellite communications and, importantly, AI ethics in telecom.
Wow, that's incredibly broad within telecom, from bedrock principles to cutting-edge and operational aspects.
Exactly the point. The aim was to give TSLAM Mini a really holistic understanding across the entire telecom domain, so it's not just an expert in one tiny niche.
It prepares it for a wider variety of tasks it might encounter.
Precisely.
Okay, let's circle back to that bespoke data set. You called it the secret sauce, and it sounds like it. The digitwin simulations, the RFCs, the SME input. How did they actually weave these together?
Well, it's a multi-pronged approach, as you said. First, the digitwin platform, and NetoAI uses it to create these really detailed virtual models of network equipment and entire network segments.
Like a flight simulator for networks.
Kind of, yeah. They can simulate normal operations, but also faults, configuration changes, traffic surges, generating realistic data showing how networks behave dynamically. And crucially, they can do this without needing direct access to sensitive, live customer network data.
Oh, that's clever. Captures realism without the privacy hurdles.
Right. Second is the RFC ingestion. They built an automated pipeline to pull in relevant technical standards documents from bodies like the IETF and 3GPP. But it's not just text dumping.
It needs to understand them.
Exactly. They use techniques like structural parsing, semantic filtering, basically teaching the system to understand the meaning and structure within these dense technical docs, so the model learns the official rules and protocols correctly.
Okay, so simulated real-world behavior plus the official rulebook. What's the third leg?
The human element. Subject matter experts. Experienced telecom engineers and architects reviewed and annotated the data. They provided insights, clarified ambiguities, added context based on their real-world experience.
Making sure it's not just theoretically correct, but practically relevant.
Absolutely. That SME input bridges the gap between the simulations and RFCs and how things actually work in the messy real world. It adds that layer of practical wisdom. So you get technical depth, standardization, and contextual relevance.
That sounds like a phenomenal way to build training data for a specialized field. So the big question, how did TSLAM Mini actually perform after all this specialized training?
Well, the paper suggests it performed very well. They used a novel evaluation approach. Instead of just relying on standard benchmarks or only human reviewers, they used another very powerful LLM Qwen 3 235B A22B as a kind of automated judge.
Using an AI to judge an AI. Interesting.
Yeah. This judge model was specifically tasked to evaluate how faithfully TSLAM Mini followed instructions and the quality of his answers on telecom-specific prompts.
And what was the verdict from the AI judge?
The results were pretty clear, according to the research. TSLAM Mini showed a, quote, superior aptitude for telecom tasks.
Superior to what?
Superior specifically when compared against larger general-purpose models like Gemma 9B and Llama 8B on telecom tasks. The paper includes figures that apparently show this quite clearly.
So even though it's much smaller, its specialized training made it better at telecom than bigger models without that focus.
That's the key finding. The bigger models might win on general knowledge quizzes, but TSLAM Mini excelled in its home turf, so to speak. It really underscores the power of domain specialization.
That's really compelling. It's not just about size, it's about focused training on the right data.
Exactly. And the training metrics support this. They tracked the training loss, basically, how many errors the model made during learning. It dropped significantly from around 2.6 down to about 0.15 over millions of training examples.
Showing it was learning effectively.
Right. And its accuracy in predicting the next piece of telecom-related text, the mean token accuracy, climbed to nearly 97%. That indicates it really assimilated the patterns and knowledge of the telecom domain.
Okay, so the training clearly worked. This brings us back to that claim, possessing the intelligence of a network subject matter expert. What does that mean in practice?
It signifies that this focused training, using that rich, curated data set, has imbued the model with a deep, functional understanding of telecom concepts, protocols, troubleshooting, best practices.
So it can reason like an expert.
That's the idea. It can understand complex questions about telecom scenarios, analyze them, and generate responses that are accurate, relevant, and context-aware, much like a seasoned human SME would.
So if I asked it about, say, troubleshooting a tricky MPLS label issue or planning a 5G network slice deployment,
It should be able to provide a coherent, knowledgeable, and useful response, drawing on that specialized training. This SME-level capability is what makes it potentially so valuable across those 20 use cases we talked about.
right, it can assist with everything from configuring devices to diagnosing faults to security analysis to automation tasks because it understands the underlying principles at a deeper level.
Precisely. It's not just pattern matching on keywords, it's applying learned knowledge. The goal is to provide precise, context-aware, and importantly, actionable insights for complex telecom challenges.
Which could really help drive towards more intelligent, maybe more resilient, even more autonomous network operations.
That's certainly the potential. It could significantly change how telcos manage their networks, diagnose problems faster, and roll out new services more efficiently.
Now, something else mentioned was parameter-efficient fine-tuning PFT, and specifically QLoRa. Why are these techniques important here?
Good question. PEFT methods like QLoRa are really crucial for making this kind of specialized fine-tuning practical.
How so?
Well, fine-tuning a huge model traditionally requires massive computing power and data. PFT techniques are much more efficient. QLoRa specifically is clever because it only updates a small fraction of the model's parameters during fine-tuning.
So you don't need to retrain the whole giant thing.
Exactly. And it also uses quantization in this case, representing the model's numerical weights using only 4 bits of precision instead of, say, 16 or 32.
Making the model smaller and faster.
Yes, both during training and for deployment. It means you get substantial training efficiency, as the paper puts it. Less cost, less time, but maybe even more importantly,
Yes.
it opens the door to deploying these specialized models on hardware with limited resources. Think edge devices, maybe even equipment within the network itself.
Wow, so you could have this SME-level intelligence running closer to where the action is, not just in a big data center.
That's the potential. It makes this specialized AI much more accessible and deployable in real-world telecom environments.
That efficiency piece sounds critical for practicality.
It really is.
Okay, so let's try and wrap this up. If you had to boil down the core message from our deep dive on TSLAM Mini, what would it be?
I'd say the main takeaway is this. For complex, specialized industries like telecom, building domain-specific models like TSLAM Mini is key. Fine-tuning them on high-quality, relevant data using efficient methods like QLoRa makes them significantly more effective than just relying on general-purpose giants.
And the result is a model that can operate with the intelligence of a network SME.
Yes, that ability to function at an SME level is what makes it so promising for tackling the diverse range of AI applications needed in the telecom sector. It understands the nuances.
It really does sound like a potential step change. Did the research mention where this is headed next? Future directions.
It did briefly. They're looking at ways to boost its reasoning even further, possibly using reinforcement learning from human feedback, RLHF. That could help it handle even trickier diagnostic or optimization problems by learning directly from expert corrections.
Refining his expertise even more.
Right. And they're also working on novel PEFT techniques, maybe even more advanced quantization methods to push efficiency further, especially for those resource-constrained devices, without losing performance.
Very interesting. So continued refinement and making it even more deployable.
Seems to be the plan.
Okay. Well, as we finish up, here's something for you, our listeners, to think about. We've seen how this tailored AI approach shows real promise in the specialized world of telecom. Where else could this apply? What other complex industries, maybe finance or healthcare or manufacturing, or even your own field, could benefit from AI models that aren't just generalists, but meticulously trained, domain-specific experts? It certainly makes you think about the future landscape of AI applications, doesn't it? Thanks for joining us on this deep dive.